Hello everyone. Myself Mr. S.M. Ganwat working as assistant professor in mechanical department at Sharad Institute of Technology College of Engineering EDRA. In part 2 of atomic structure and interatomic bonding, we are going to discuss what is quantum number, then we are going to discuss the electron configuration, and we are going to discuss the periodic table. These 3 points we are going to discuss under this session of atomic structure and interatomic bonding part 2. We will start with our first point, that is quantum numbers. Using wave mechanics, every electron in an atom is characterized by four parameters called quantum numbers. The size, shape, and spectral orientation of an electron's probability density are specified by three of these quantum numbers. Furthermore, Bohr energy levels separate into electron subshell and quantum numbers dictate the number of states within each subshell. Shells are specified by a principal quantum number, which is identified by letter n, which may take on integral values beginning with unity. Sometimes these shells are designated by letters capital K, capital L, capital M, capital N, capital O, and so on, which corresponds respectively to n is equal to 1 to 5 and so on. The table is going to show you the number of available electron states in some of the electron shells and subshells. The first column consists of principal quantum number, which is indicated by letter small n. Second column consists of shell designation, which consists of the values k, l, m, n, subshells, number of states, number of electrons per subshell and per shell. Now we are going to discuss this particular table. The quantum number dictates the number of states within each subshell. Shells are specified by a principal quantum number, which is identified by letter small n, which may take on integral values beginning with unity. Sometimes these shells are designated by letters K, L, M, N, O, and so on, which corresponds to respectively to n is equal to 1, 2, 3, 4, 5 as indicated in table. Also note that this quantum number is also associated with Bohr model. This quantum number is related to the distance of an electron from the nucleus or its position. The second quantum number L signifies the subshell, which is denoted by a lowercase letter as S, P, D, or F. It is related to the shape of electron subshell. In addition, the number of these subshells is restricted by the magnitude of small n. Allowable subshells for the several n values are also presented in table. The number of energy states for each subshell is determined by third quantum number, small m. For an S subshell, there is a single energy state, whereas for P, D, and F subshell, 3, 5, and 7 states exist, respectively. In above, in the absence of an external magnetic field, the states within each subshell are identical. However, when a magnetic field is applied, these subshells states split, with each state assuming a slightly different energy. Associated with each electron is a spin moment, which must be oriented either up or down. Related to this spin moment is the fourth quantum number, that is ms, for which two values are possible: positive half and negative half, one for each of the spin orientation. Thus, Bohr model was further refined by wave mechanics, in which the introduction of three new quantum numbers gives rise to electron subshells within each shell. A comparison of these two models is already discussed in last session. Now, figure is going to show you the schematic representation of the relative energies of the electrons for the various shells and subshells. Now, a complete energy level diagram for various shells and subshells using the wave model is shown in figure. Several features of the diagram are worth noting. First, the smaller the principal quantum number, the lower the energy level. For example, the energy of 1s state is less than that of 2s state, which in turn is lower than 3s. Second, within each shell, the energy of subshell level increases with the value of L quantum number. For example, the energy of a 3D state is greater than a 3p, which is larger than 3s. Finally, there may be overlap in energy of a state in one shell with states in an adjacent shell, which is especially true of D and F states. For example, the energy of a 3D state is generally greater than that of 4s. We will repeat this particular concept once again. Several features of this particular diagram we are going to discuss. First, what we are going to discuss is the smaller the principal quantum number, lower the energy level. Means the principal quantum number is smaller, you will get energy level at the lower side. For example, the energy of a 1s state is less than that of 2s. Means principal quantum number is smaller, the lower the energy level, or energy level is at the lower side for smaller principal quantum number, which in turn is lower than again 3s. The same fundamental is utilized, that is, smaller the principal quantum number, lower the energy level. Then the energy of a subshell level increases with the value of the L quantum number. For example, we are going to discuss the energy of a 3D state is greater than 3p, which is again larger than 3s. Finally, there may be overlap in energy of a state in one shell with states in an adjacent shell, which is especially true for D and F states. For example, the energy of 3D state is generally greater than that of 4s. Now we are going to discuss the next point, that is electron configuration. In previous discussion, we are dealing with primarily with electron states, that is values of energy that are permitted for electrons. To determine the manner in which these states are filled with electrons, we use the Pauli exclusion principle, another quantum mechanical concept. This principle stipulates that each electron state can hold no more than two electrons. Once again, I repeat this Pauli exclusion principle. It stipulates that each electron state can hold no more than two electrons, which must have opposite spin. Thus, S, P, D, and F subshells may each accommodate respectively a total of 2, 6, 10, and 14 electrons. And the previous table that we have discussed already summarizes the maximum number of electrons that may occupy in each of the first four shells. Of course, not all possible states in an atom are filled with electrons. For most atoms, the electrons fill up the lowest possible energy state, in the electron shell and subshell, 2 electrons per state. The energy structure for a sodium atom is represented in figure. When all electrons occupy the lowest possible energies in accord with the foregoing restrictions, an atom is said to be in its ground state. However, electron transition to higher energy states are possible. The electron configuration or structure of an atom represents the manner in which these states are occupied. In the conventional notation, the number of electrons in each subshell is indicated by a superscript after the shell and subshell designation. The major point in this discussion are: the first major point is electron state, second is Pauli exclusion principle, third is ground state, and fourth one is electron configuration. We'll shortly discuss these again. Electron state, it is nothing but value of energy that are permitted for electrons. Also, we are going to discuss Pauli exclusion principle. This principle stipulates that each electron state can hold no more than 2 electrons, which must have opposite spin. Then we are going to discuss the ground state. When all electrons occupy the lowest possible energies in accord with the foregoing restrictions, an atom is said to in its ground state. Then we are going to discuss the electron configuration. The electron configuration or structure of an atom represents the manner in which these states are occupied. Now, in conventional notation, the number of electrons in each subshell is indicated by superscript after the shell subshell designation. For example, the electron configuration for hydrogen, helium, and sodium are respectively 1s1, 1s2, and 1s2, 2s2, 2p6, 3s1. Electron configuration for some of the more common elements are listed or they are shown in figure. At this point, comments regarding these electron configurations are necessary. First, the valence electrons are those that occupy the outermost shell. These electrons are extremely important, as will be seen. They participate in the bonding between atoms to form atomic and molecular aggregates. Furthermore, many of these physical and chemical properties of solids are based on these valence electrons. In addition, some atoms have what are termed stable electron configuration, that is, the state within the outermost or valence electron shell are completely filled. Normally, this corresponds to the occupation of just the s and p state for the outermost shell by a total of 8 electrons, as in neon, argon, and krypton. One exception is helium, which contains only two 1s electrons. These elements are the inert or noble gases which are virtually unreactive chemically. Some atoms of the elements that have unfilled valence shells assume stable electron configurations by gaining or losing electrons to form charged ions, or by sharing electrons with other atoms. This is the basic for some chemical reactions and also for atomic bonding in solids. Under special circumstances, the s and p orbitals combine to form hybrid sp orbitals, where n indicates the number of p orbitals involved, which may have a value of 1, 2, or 3. The 3a, 4a, and 5a group elements of the periodic table are those that most often form these hybrids. The driving force for the formation of hybrid orbitals is a lower energy state for the valence electrons. For carbon, The sp3 hybrid is of primary importance in organic and polymer chemistries. The shape of the sp3 hybrid is what determines the 109-degree angle found frequently in polymer chains. Now, the next point that we are going to discuss is the periodic table. All the elements have been classified according to electron configuration in the periodic table as shown in figure. Here, the elements are situated with increasing atomic number in 7 horizontal rows called periods. The arrangement is such that all elements arrayed in a given column or group have similar valence electron structure as well as chemical and physical properties. These properties change gradually, moving horizontally across each period and vertically down each column. The element positioned in group 0, the rightmost group, are the inert gases, which have filled electron shells and stable electron configuration. Group 7a and 6a elements are 1 and 2 electrons deficient, respectively, from having stable structure. The group 7a elements are sometimes termed as the halogens. The alkali and the alkaline earth metals are labeled as groups 1a and 2a, having respectively 1 and 2 electrons in excess of stable structures. The elements in the three long periods groups 3b and 2b are termed the transition metals, which have partially filled d electron states and in some cases 1 or 2 electrons in the next higher energy shell. Group 3a, 4a and 5a display characteristics that are intermediate between the metals and nonmetals by virtue of their valence electron structure. As may be noted from the periodic table, most of the elements really come under the metal classification. These are sometimes termed electropositive elements, indicating that they are capable of giving up their few valence electrons to become positively charged ions. Furthermore, the elements situated on the right hand side of the table are electronegative. That is, they readily accept electrons to form negatively charged ions, or sometimes they share electron with other atoms. Now we will just take an overview of the periodic table. All the elements have been classified according to electron configuration in periodic table. The elements are situated with increasing atomic number in several horizontal rows. We call it as periods. The arrangement is such that all elements arrayed in a given column or group have similar valence electron structures as well as chemical and physical properties. These properties change gradually, moving horizontally across each period and vertically down each column. Also, we are going to take a note of electropositive element and electronegative element. As it may be noted from the periodic table that most of the elements really come under the metal classification. These are sometimes termed as electropositive elements, indicating that they are capable of giving up their few valence electrons to become positively charged ions. Furthermore, the elements situated on the right hand side of the table are electronegative. That is, they readily accept electrons to form negatively charged ions, or sometimes they share electrons with other atoms. Now, the figure displays electronegativity values that have been assigned to the various elements arranged in the periodic table. As a general rule, electronegativity increases in moving from left to right and from bottom to top. I will repeat this concept of electronegativity once again. As a general rule, electronegativity increases in moving from left to right and from bottom to top. Atoms are more likely to accept electrons if their outer shells are almost full and if they are less shielded from the nucleus. Shielded means closer to the nucleus. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rethwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.